I'll talk about LLM foundations, continuation of what Victor covered in the first lecture. And this will be covering some of the stuff that is done for like development of LLMs after post training. So post training will cover like some stuffs which are not necessarily things that we obtain during the training phase, but that are used to even improve the capability of large language models after the initial model is trained and maybe fine-tuned, and there are a lot of additional capabilities that LLMs possess and things that can be used for different applications. So this is like a high-level overview of basic concepts and some of the trends that has been seen in the research area in the recent years. Before I start, let me introduce myself just quickly. So I'm from Birgunj and I currently live in San Francisco Bay Area. I'm doing my postdoc at Stanford. Prior to this, I did my PhD from NTU in Singapore, and I do research on like graph representation learning. How can we develop multimodal architectures for understanding rich structure data? And I've also worked in industry where I got exposed to several applications such as healthcare, social networks, etc. So the outline of this lecture session will be, we'll talk about what are emergent abilities of large language models. This is something that we see when models are scaled up and they're not observed when the models are smaller. We'll learn about chains of thoughts, how it leads to reasonings, how agentic AI, what's agentic AI framework and the promise, different examples it brings to a lot of application areas. And finally, we'll conclude with retrieval augmented generation in this first session. So let's start with emergent abilities of large language models. This will be in continuation with the previous lecture. So we saw that at the core of the development of language modeling, there is this next word or next token prediction. It allows, it's such a simple but very powerful framework that it allows a large language model or any language model to learn a lot of things without doing any supervision. So for instance, if there's a text that says in my free time I like to, so the goal of the language model is to give highest probability for verb tokens. So in this example, there are 4 words that's kind of just as a toy example. So there's like a, food, play, and zebra. So we know that after the word to, we need a verb word. So when the language model is kind of learning to predict these next tokens in such a way, it's trying to learn grammar of a language. Similarly, it also learns facts. For example, in this case, the capital of Nepal is, and the task is to predict the next word. There's a high probability of the word Kathmandu, so it's trying to learn facts. We have different other examples. In this case, the next word prediction is trying to predict something that can come together with giraffe, tiger, and there's a background zoo. So in this case, if the model is giving a high probability for the word zebra, it's learning lexical semantics, like what kind of words come together in a sentence and according to the context that it is introduced for. A lot of like tasks such as sentiment analysis also can be considered as like can be formulated in the next word prediction framework. Like I was in a movie, I was on the edge of the seat my whole time the movie was, and the movie is good. So we don't have to have a separate model, but rather the next token prediction or next word prediction is also enabling learning these kind of tasks, which maybe 5 years or 10 years ago, there was a different area of like developing sentiment analysis models or maybe movie rating models at that time. So what's happening is this very simple framework of having next word prediction, for which you don't need supervision. You can just take the whole internet's text and create a training corpus. You are enabling massive multitask learning. We have just one single objective that is allowing the language model to learn grammar, different facts, lexical semantics, semantic analysis, movie rating, maybe maths, maybe trying to autocomplete some codes under just one framework, and much more. So this is the kind of simple yet very powerful objective that language modeling have. And now we're coming to the emergent abilities. So what's important to notice that at scale, even more is achieved by just this next token prediction. And how do we scale these models? So if you recall from the previous lecture, there are three things: model parameters, data size, and compute. So these are the three dimensions along which language models scale. And we can kind of remember this with A, B, C. So language models scale with A, architecture; B, big data; and C, compute. And there's a very interesting, there's a very classical paper called Scaling Laws for Natural Language Models, Neural Language Models, which tries to do an in-depth understanding of how does models scale across all these different dimensions. And there's a very predictable scaling that happens. Like as you increase the model parameters, there's a direct proportionality of like how the loss decreases with respect to the number of parameters, that's denoted by n here. Similar with the dataset size, that's denoted by d. As you increase the dataset size for training, the loss decreases predictably. And same with compute. As you increase compute, PF here is petaflops, which is 10 to the power 15 floating point operations, and per day means like I think it's around 86,000 seconds per day. So this is like a very standard unit of petaflop days in terms of compute. So as you give more compute to the models, also like there's a chance to decrease the loss of a model. So this is like a way to, like, these are all the dimensions across which scaling happens. And we see a lot of different phenomena, and this is what the first part I'll be talking, like emergent abilities of large language models, which is to kind of convince that we get capabilities in models only if they are large. And that's what the definition says, like an ability is emergent if it is not present in smaller models, but it's present in larger models. And I'll show some examples on what this means. And this was done in a very classical paper called Emergent Abilities of Large Language Models from 2022 that does a kind of in-depth study on what emergent abilities is, like why there's a need of scaling models up without training, how we can extract and exploit more performance from the same models of same scale, what are the ingredients. So this is what we're kind of entering at. So how this emergent abilities is kind of being understood is through few short prompting. So I guess all of us know what's a prompt. So a prompt is input that we give to a language model for which it will generate some next tokens, and it will keep on generating until it encounters an end of sequence or similar kind of tokens. So a prompt is just the input. Few short means the prompt includes exemplars for the task. For instance, if the prompt is about trying to find out what is the sentiment of a movie, so the few short means we would give examples of, like, if a review says something, what is a sentiment. So in this case, if the review is this movie sucks, the sentiment is negative. So this is one example. So it can also be called one shot prompt. We can have like one shot, two shot, or even multiple if we include multiple examples in this prompt. So this is a definition of like how a few short prompt is prepared. And when this is studied, like what is observed is like if we have tasks like these, if it achieves random accuracy for small models but above average or above random accuracy for large models, then the task is emergent. So in this case, for instance, if I were to give a prompt like this to a model, I would see whether it's performing good or not. And the finding that was observed is on small models, the performance is not good. It's probably random. But on large models, if you give some examples in the prompt, it can predict, like for unknown case, for example, in this case, like what will be the answer. And this is a very toy example of sentiment analysis, but you can say that with a group of friends, I have so and so situation, and then for this situation, this was what happened. So what should be done for a new situation? So those kind of cases as well. That's also an example of few shot prompting. You'll get some performance more than random in large models, but not in small models. So this is what is called emergent, and they are very how to say, like the examples such as in this case, if you increase the number of examples in the prompt, they are also like performance increase. And like this whole thing of few shot prompting, there are other terms to kind of understand this. One is called in context learning. Like whenever I'm asking an LM to give me outputs and I'm giving examples, I'm providing a context through which LM is trying to understand what should be the prediction, or what should it generate for a new example case. So in this case, for example, if the prompt is translate English to French, and there are 3 examples that I've given, like sea otter translates to something, peppermint and plush giraffe translates to something. So what should cheese translate to? So this is like a prompt which has 3 examples, and I'm expecting the LLM to learn through these examples, and that's what is called in context learning. So these are just some backgrounds. Now I'll show what were the results of these studies. So there's a benchmark called Big Bench, which has around 67 tasks. I'm sorry if like the text is not clear at the back, but I can read some of those tasks. So some of the tasks are like Hindu knowledge, like it's kind of a fact recall task, a lot of question answering tasks, arithmetic coding tasks, social IQ, physical intuition about like how if you throw a ball, like what happens, like it's something relates to physical intuition. So there are a lot of tasks in this benchmark, and similarly there's another benchmark called MMLU, which is very popular in the evaluation of large language models as well as even multimodal models. So it also has a lot of tasks that relates to like how what kind of knowledge there should be for people who have graduated high schools. A lot of domain like marketing, sociology, foreign affairs, physics, engineering. So MMLU has a lot of those tasks as well. So these are all the areas where this emergence was kind of evaluated with few shot prompting. And some examples are like if the question is the Hindu deity human is depicted as which animal, and there are multiple choices, and the answer is monkey. So if you see this example, again, it's not, I understand that it's not very clear at the back, but I can read some of those things. So there are 2 things to observe here. On the y-axis is the performance. On the x-axis, there's model parameter count. And different models here show examples of 0 shot, 1 shot, 2 shot, even 3 shot, and different models with respect to parameter size. So the observation is that as models increase, there's a sharp, like the model parameters increase, there's a sharp increase of performance. So for example, if we were to see this, maybe like a Palm, which is a language model from Google, prior to Bard and Gemini, they had Palm language models. So they get a lot of like, they get impressively good results from the average rate of performance, which is around 60 here. If they use Palm and then they have like 1 shot, 2 shot, 3 set examples here. So some examples here can be a different knowledge from the benchmark and their answers, and then the task is to predict the answer for this. So 2 things help. One is the model parameter count. If it's large, the model is able to give answer correctly, and then if there are more examples. So it's called emergent ability of a language model, because in the smaller models, even if I'm giving examples, the model is not able to predict the correct answer. But if the model is large and I give the same number of examples, we get answers which are better than average. So this is happening without training the model. So if let's say you have been given a model, you don't need to fine tune, or you don't need to kind of train to a different scenario. You can just give examples in the prompt, and then you get good answers. So this was very very like promising to see first somewhere around 2021 and 2022, that kind of gave promise towards the development of even largest language models. Because if let's say you have a model and you want to make it adapt to different tasks, the traditional knowledge was you must have to fine tune, but with this you don't need to fine tune, and there's a potential of, or maybe there's a promise of even investing on very large language models, like scaling these models even up. So that was kind of the observation with this kind of work. And there are other examples as well. Like if let's say I were to define a task, in this benchmark is modified arithmetic, which says that if I were to define a task that is, for example, in the following lines, the symbol arrow represents a simple operation. And I'm not saying this model what this operation is. I'm just giving examples that 100 plus 200 gives 301. 64 plus 138 gives 203, and so on. I mean, what these examples are saying that you're adding two numbers and increasing the total value by 1. So in the case of 100 and 200, the addition gives me 300, but the arrow says the answer is 301. So the model is able to infer these things, and for a new example, it will also understand the logic that the task here is a hypothetical task of adding two numbers and increasing their result by 1. So this is like an example of modified arithmetic. Later, there's a link that I have in all these slides. You can go and play with these. These are like, you don't need to understand much like in terms of like how to set up when you want to play with these kind of models. You just, they're benchmarks, they're prompts. You can play with like some open source models or some APIs if you can, if you want to play with. But you'll see like all these prompts, examples, and tasks that it can solve. But the main thing to kind of understand from this slide is that there is this operation which is not verbose, it's not being said, but we just have examples. In this case, like I think there are 5 examples, so it's like 5 short, and the smaller models cannot do it, but larger models can do it. And there are other examples, debugging of code, logical sequence, like if you're given a sequence of like something happened, at this parallelly something else happened, so what's the conclusion? So these kind of things as well, and we see the same, like there's the same observation of like emergence in large language models. So yeah, the conclusion of like the emergent abilities was, as models scale up, we see this ability. So that's like a argument of why there should be more investments in large language models in terms of scaling. And at the time of doing this, the models used to be like, the largest models used to be like 100 billion parameters or so. But right now, most of the closed source models like Gemini or ChatGPT, Anthropic, we don't know what the number of parameters they have, but there are like very strong guesses that some of them are even like close to trillion parameters. So the intuition behind doing this was, in larger models there was more these emergent abilities, so you don't need to kind of train it if you want to use it for a task off the shelf. Yeah, so this is what I was saying. So there are things that language models can do. It increases in a regime of large model parameters. Having said that, there are also some criticisms to this. Like there are some paper, and Victor had this in the first session as well. So in some cases, like there are studies and questions which says that models don't show emergent abilities. Instead, what is happening, there's a metric like in the previous all these examples, many of them are like multiple choice questions, so there's accuracy. Accuracy is kind of a not a continuous metric, but rather it's just like we'll see that if the highest probability has a correct option. So for example, if I have 2 options and then the probability of one how to say, like one label is like 0.6, I would convert this to just 1. So it's not a continuous metric. So this paper kind of shows that the observation that we had in all of these was, there's a very sharp increase of performance when the models go large. But when they try to change the metric, it's not as sharp. So on the top, these are like original scores of emergent abilities, and the thing to notice here is that the performance gain is sharp. In the smaller models, it's kind of utterly fails, and then it improves when the scales increase. But when they change the metric to something which is like continuous, for example, the token edit distance, you can check out this paper if you're interested more in detail. But I just want to show here the trend is that instead of this kind of sharp curve, there's a very smooth curve actually in terms of when the metric is continuous and not just accuracy. So there's a smoothness here versus here. There's a smoothness here versus like the sharpness here, and so on, the smoothness here versus the sharpness here. So this is just some kind of paint the picture of like what emergent abilities are. Moving ahead, because emergent ability is something like we got to learn a couple of things. One is large scale, and second is I can make large scale models performance even more, like I can squeeze out more performance by doing few shot prompting in large scale models. So there was some more investigation in how to design better prompts, and that's where chain of thought was very impactful. Like this was a work by Jason Wei. He was a resident at Google Research, the brain team. And they kind of explored this. Again, this if you read this paper, there's no model development, no training, but just trying to understand how can prompting help to extract or squeeze the highest amount of performance from a language model. So when we do certain tasks, the traditional prompting was you give a question, and let's say let's observe that this is a few shot prompt where I have one example and then I have a question and I want an answer for that new question. So I didn't explain what was the reasoning behind the first answer, but that was like standard few shot prompting. But if I give a chain of thought, like how the first example gives this answer 11, if I try to explain the model, then without doing anything on the model, I can get the correct result. And that's kind of like it has kind of ingrained into people's habits as well. Like whenever we prompt and then we want to get even better results, if we explain certain rationale behind and give examples, we often get good results. So this was what chain of thought kind of found out about large language models and this ability, that a series of intermediate reasoning steps in the prompt in the few short exemplars can significantly improve LLMs without doing anything else. And the reasoning steps can be included in the prompt, as it's highlighted in the case of like these blue examples of solving these mathematical word problems. When we give these examples, the large language model's inference process or the decoding process also ends up generating chains of thoughts to actually give the answer. So in this case, like in the prompt, we had examples of like what is the chain of thought for doing this. So the output, you can notice that the model is also giving output like in the decoding, not just the final answer, but its thinking process as well. So there are a lot of new things that will emerge from here, and one of that is reasoning. So this like models performing better with reasoning steps, like intermediate steps, was kind of like a precursor to reasoning LLMs. And I'm sure like every one of us use LLMs, ChatGPT, Anthropic, Gemini, whatsoever, and we would have observed since last 1 year, we have reasoning in most of these LLMs. Like you type something, the model gives intermediate steps, and then only it gives the final answer. So the remarkable improvement through these chains of thought prompting was kind of what informed that we should actually do reasoning. But I'll come that to later, but just some more about chain of thought. You'll notice like there are like a lot of benchmarks, math word problems, common sense answering, some strategic question answering, understanding some formal data such as date, facts, sports, coin flip, some more like lexical tasks as well. And what can be seen is that there's a different prompt engineering kind of happened in 2021, 2022 when like if there's a benchmark, prompt engineers were kind of deployed in trying to provide rationales of like how a question is answered in the few short examples. And this is just to show some examples of like what are these chain of thought in the few short prompts and even in the answer as well. And yeah, so the key thing is like at a given model scale, if we are not using chain of thought versus you're using chain of thought, the use of chain of thought significantly elevates performance, and it can be seen in precisely this two example. So there's a benchmark called GSM 8K, which is a benchmark of math word problems. And if I'm using the same model like PaLM, which is like a precursor of like a Bard and then Gemini that Google has now. So at that time it was like 500 billion parameters, and if there was no chain of thought, it was having like a performance of roughly 18%, but only by using chain of thought they elevated it to 57. This was remarkable because there's no additional training or fine tuning, but just rather only prompt engineering and having better chains of thoughts. So there was a very significant elevation of performance in this. And another observation was, which relates to the emergent abilities, that the chain of thought prompting only helped large language models. It didn't help smaller models. Like if you see the math word problems, the other benchmarks as well here. On the smaller model size, if the model of standard prompting versus chain of thought prompting are compared, there was not much elevation of performance in the smaller model, but only in the larger models. So this was also one key insight from this series of work. And coming to limitations. So the good thing about chain of thought giving good performance is that we don't need to train or fine tune the model. But the bad thing is that we have to do prompt engineering. And it again goes back to, now we started language model from the previous lecture. We started that, okay, we have self-supervision, we don't need to supervise things, but now we are again coming back to supervision. We need supervision, we need people and domain experts to kind of draft prompts, and these prompts should not be noisy. So there's a limitation of this, but also like what kind of strategies to use in prompting. So for example, there was this paper from the same team, same brain team of Denny Zhao and others. They have like different strategies. Like this was like breaking down a problem into sub-problems, like decomposing a question into subsequences, and then sequentially solve those sub-questions. So this was also one strategy that was used to get better performance, and this is more like a further like depth of like how chain of thought can be better designed. In a series of conversations, the language model will give a good answer. So this is also kind of again ingrained into habits of how people use LLMs. Like if I have a very complex task to solve, I can think of breaking down them into sub-problems, and then maybe step by step in a series of conversation I would solve that. So again, different engineering. There's no how to say, there's no one saying that this is the best strategy, but these are all empirical how to say, like hit and trial kind of studies, but yeah, giving good performances. So it's good, but also a limitation that you don't know what's the deterministic best way to do things, and a lot of effort needs to be kind of spent into prompting. Like if I want to solve a very complex task, I want to solve in the next 1 minute instead of spending the next 30 minutes trying to be imperative about it and then find out what are the steps, how to break this problem into different steps. So just to highlight some limitations here. And another issue with chain of thought is, if let's say I have a prompt engineer that gave me the rationale, and then there was one mistake. Like in this case, there's one mistake, such as there's someone who has $65 in the bank, there was a $15 deposit and then $4 withdrawal. What is the bank balance? So if this was not there, the answer was correct. But now there's an irrelevant sentence that was inserted, that someone's monthly rent is something else. So the answer, the LLM, while giving the answer, also considered this as an expense, because of which the model gave the incorrect answer. So there are these kind of like pitfalls in chain of thought as well. There are other examples or improvement to chain of thought. So in kind of addressing the limitation of the manual design of prompt in chain of thought, there were some works that showed we can actually do zero-shot prompting as well. Like instead of having prompts, if I have a task and if I just say, let's think step by step. Imagine you're using LLM to do something, and then you just use the word, let's think step by step. the model is suddenly performing much better than not using it. And This is called zero shot chain of thought. So there's a chain of thought that is kind of triggered, or maybe like there's a guidance provided here in the prompt, but there's no need of like designing designing reasoning steps, because you can use the same less thing step by step across domains, and the model is certainly performing better. So this was one of the work that addresses some of the limitation of manual reasoning design or manual chain of thought design that I mentioned in the previous slide. There's other prompting techniques as well. One of them is like analogical prompting. So let's say when I'm asking LLM to do a task, I would kind of nudge the LLM to find out similar examples or similar questions, and then solve those first before answering the question that I'm asking you for. So the LLM will automatically generate examples and do things. So this is also one way to address the limitation of manually designing chain of thought prompts. There are some other ways to get even more performance. So one thing is called self-consistency, which means I will have multiple reasoning paths, and I will cut out the ones which give me the wrong answer, and I'll only use the ones which give me the right answer and make a majority voting of it. So that's also one of the ways. So there are actually tens of, like maybe hundreds of work that explore different ways of doing prompting, maybe improving chain of thought. So I mean, you can definitely look into it more. So, but the goal of this is to kind of highlight some of the representative works that has led to like the development of LMs as recent as, let's say, 2025. So that was chain of thought, and like I mentioned, this was a precursor to reasoning models. Now we have a new framework. Previously we had next token prediction, which gave question and answer, but now we have an additional thing in between that is amazing. Like if we just add intermediate steps in the whole framework, we can get even more capability of language models. And think about this like a human. Like when you are given a task, you think before answering. So that's kind of the loose motivation of doing this. So the intermediate steps here before answering a question is what is called reasoning. It's not reasoning per se like how humans understands. Like how LM does reason is still next word prediction, but instead of having to answer the question directly, there's a emphasis given on the generation of intermediate steps before coming to the final answer. So that's reasoning in LLMs. It's still next word prediction. It's still it's kind of intermediate steps before the final answer. It's a series of tokens. It's not human reasoning in terms of like whether the LM is actually understanding something or not. So just kind of clarifying this for the definition purpose. And there now comes like two categories of LLMs. So prior to 2024, we had LLMs that give plain response for a task. Now we have two classes of LLMs, and in most of the LLM interfaces that you are seeing, like ChatGPT, Gemini, or others, even Claude, you can enable reasoning. So when you enable reasoning before coming to the final answer, the model gives rationale, which is the intermediate steps before coming to the final answer. And there can be like cases where it doesn't mean that you for correct answer you must use reasoning. You may not use reasoning and still get the correct answer. That's why like also from a UX or UI perspective of how these LLMs are kind of released as products to the public, there are these like toggles where you can activate the reasoning versus not activate, and stuffs like this. But now we have a new category of like very powerful AI systems which are called reasoning LLMs. It started primarily with OpenAI's O1, and that the development of O1 involves folks that actually develop chain of thought reasoning. There's that was one of the first reasoning models. Now we have their successors like O3. We have open source reasoning LLMs such as DeepSeek. We have Gemini thinking, and a lot more. So now we have reasoning LLMs that do one thing at its core, among other things. I won't be able to kind of go into all of these details. And also this is a disclaimer like for this whole session. So the goal is kind of touch on different topics and what's important, and kind of understand it as a story of like how we are kind of improving LLMs after doing the training stuff in the first lecture. And many of these things are very deep, very even still very active in exploration. So yeah, so I'm just trying to highlight like what's important, what happened, what was intuitively important, the key insights. So in reasoning, what was important is the inference time scaling. So we saw previously when LLMs were showing emergent abilities, or maybe doing the scaling or training part, they were scaling in terms of ABC, the model architecture, the data, and the compute. But now we can do test time compute. Like inference time scaling is kind of allowing an LLM to dynamically allocate additional compute at model inference time, and this additional compute can be chains of thoughts. So nowadays, when, for example, if you use a one model and you have a question, it does some intermediate reasoning for the product, like for the UI UX purpose. The models may obscure some of the chain of thought, some of them they reveal, and then they give the final answer. So this is inference time scaling. Like you're scaling the model to gain more capabilities by having chain of thoughts at inference, and this is dynamic. Yeah, so this is like inference time scaling, and there are a lot of ways to achieve this. I'll kind of show some of the things here, and like how it's achieved. So the setup is that we have an input problem and we need the final answer, and these are the reasoning, like the intermediate steps, or they're also called thinking tokens, are what the reasoning is. These are given by an LLM, which is also called policy model in the lingo of like reinforcement learning, that kind of trains or improves these models during the inference. And the thinking tokens or inference tokens may depend on a reward, and I would like to link the DPO and PPO, which Victor mentioned in the previous slide. So those techniques are actually used to develop models, like reasoning models, and it's applied in kind of this stage actually. So there are three key things here when the model is developed at inference time scaling. One is the reward function. The second is like what is done during the inference, given we have a fixed reward or policy model. And the third, how are these models developed? So the reward function tells whether a model's response is going in the right direction. Like if you say something and you're getting a feedback, like if LM tells something, the LM is giving some feedback, and these feedbacks can be fed back, fed into the model improvement. So we need a reward function that gives this feedback. At times it can be like non-statistical functions, for example, code executors, some syntax checkers, and at times it can also be a neural network, for example, a classifier that tells whether these thinking tokens make sense or complete nonsense, like among those things, like whether the reasoning steps will lead to an answer. And oftentimes we also can use the LLM itself as a judge. So that's a neural network. So reward function can be either of these, but the main intuition or main goal is to make sure to give a feedback in the development of reasoning LLMs, to tell like whether the model's reasoning traces are going in the right direction. And the rewards can be binary or continuous. They can be learned or unlearned as well. Like learned was an example of LLM or the classifier. Not learned was the example of like code execution and so on. And I'll give some examples later for that. There are also some reward mechanisms that may work with partial thinking tokens, like you haven't explored all the intermediate steps, but you see step by step partially. For example, if to solve some task, if a model starts reasoning, and after maybe looking at 50 tokens or 500 tokens, you realize, no, this is the bad path that the model has chosen. So there are also some reward mechanisms that can tell whether these are good or bad, like whether that reasoning path is good or bad. So yes, there are some reward mechanisms which can work with just part by part, and that's called process. Like that's come into the category of like PRMs, which is called like process reward models. And others are like outcome reward models, for which we see the end outcome and then give a reward to the LLM. Now the second part, like what is done during inference. So when a model's inference time scaling is kind of the development is happening. The LLMs generate responses. So there are multiple ways to kind of understand or maybe consider how to operate or process on these responses. So one of the very basic is like you can generate 10 examples and verify which of the reasoning traces among these 10 examples give to the correct reward, and train the model on that. There are like some beam search techniques, some look ahead search techniques, which may involve some backtracking or rollback as well. So there are multiple ways to do this, and some of these literature actually are a lot of guessworks. So for example, many of the reasoning models that we use in a day-to-day basis now are closed source, so no one knows how these models have been developed. So there are some of the just trying to understand what's working under the hood, but we may have to take these things with a pinch of salt when we try to understand like how reasoning models work. But yeah, these are some of the things that can be used. And how do we train these models now? So training these models is basically saying that when I want a model, I want an LM to have correct reasoning steps and give me the correct answers. So if let's say this is my space of correct answers, some reasoning paths may lead to somewhere else, which is an incorrect answer. Some reasoning paths may lead to the correct answer, even though the reasoning tokens can be completely nonsense. So the problem here is that from going from a question to an answer space, there can be non-trivial explosion, because it's basically like a giant graph or tree of tokens, and there will be combinatorial explosion. So there are a lot of techniques that is used to kind of address this. So one of the things, like which I mentioned earlier, like you generate n chain of thoughts, check which one is successful, and train on good ones. For example, this is my question, this is my answer, and my answer space is this. So we see that there are like 5 examples here, and only one here is correct. Others, all chain of thought leads to bad answers. So I can train on the good ones with reinforcement learning. There's another very landmark work which is called self-taught reasoner. It was by Eric, who is now at XAI or something. He used to be a student at Stanford. So they call this self-taught reasoner, which is like bootstrapping reasoning with reasoning. So you ask a LM to generate rationale and then see whether the answer is correct or not. If it's correct, then try to use it for fine tuning. If it's incorrect, then give a hint and again generate a rationale and then use it back to the model. So if you look at this, there's a lot of like self loop kind of going on here, and that's precisely it's called like self-taught reasoner. But the goal is to kind of like use chain of thoughts, maybe to use multiple chains of thought, and then like based on whether the answer is right or not. Like here I mentioned like train on good ones. Here, even it's wrong, there is some sort of like addressal happening, but and that feedback is kind of processed back to the model. But yeah, this is like the intuition on how I'm teaching or how I'm improving the LLM to be a reasoning LLM. There are process rewards. Like I mentioned, there was like we can also have partial thinking traces to train a model. So there are also called process reward models, and during this chain of thought, check whether like certain traces lead to the good answer, and if the final versions are successful, train on the good ones. So this is also one way. And yeah, so this was just to show that how the reasoning models are developed after it was found out that okay, chain of thought was good for model improvement. And I'm skipping most of the details for the sake of time, number one, and number two, like you'll see some ways of like how reinforcement learning works in some of the lectures tomorrow. So when we don't have the right answer, but we know whether something leads to a correct stage or correct action, something leads to a incorrect action, in that scenario we do reinforcement learning. So that is like the most predominant way to develop reasoning models. Yeah, there is a separate there are separate sessions on that. But here the goal is to kind of show from the higher level like story perspective, like how these are used for what kind of key insights and intuitions are used for reasoning model development. So now the final two things, but these are like where most of the current frontier is kind of progressing, and people talk about whether AI will replace humans, AI will replace some professionals. So that's where kind of the industry is heading at. And I won't be, I think we have like maybe 5 or 10 minutes. I will just quickly go through these two concepts. And I mean, these are, if some of you are kind of looking maybe 3 to 5 years down the line, like what you should work at, there are a lot of like open challenges in precisely these two areas, or specifically like the agentic AI as well. So what is an agentic AI like framework? It's a system that can autonomously break down complex tasks into steps and take actions to accomplish the objectives of each of those steps. And if we recall, from the reasoning, we had question and answer, and there were some intermediate steps. So this is essentially an abstraction of any workflow that we do. I want to cook something in my kitchen. I want to clean clean this lecture hall. I want to send an email after understanding a paper to my advisor. I want to report how to say, inference or analysis of some data that I have collected from experiments. Everything can be packed into this workflow. So this is very generic, and it unlocks like new multi-trillion opportunities in terms of like where AI is heading next. And one key thing is like, when we have, like until now we were talking about LLMs, so we had questions, reasoning steps and answers. All of these were tokens, right? And there's a vocabulary of tokens that came through some tokenization approach, for example, the byte pair encoding that Victor was mentioning earlier. So now if I were to take tools and external knowledge in that token space, I can solve, like this above pipeline can simulate any multi-step task. Let me give you an example. For instance, I want LLM to use my browser, and in my browser, I have certain like maybe 100 or something keystrokes that I type in my browser address bar, and a mouse with a left, right, top, down, or maybe some coordinate-based pointer. So if I want an LLM system to use a browser, I need certain tools that it can take actions. And if I have those tools as part of my tokens, or maybe some vocabulary that is part of this question, intermediate steps and answer, then I can have browser that is being used by AI. And then we have like Comet browser, which is what I'm using right now. I mean, it's one of the agentic browser that we have. But to understand this, you can see that if certain tools and if certain tools can be included in the workflow, we can have an AI user browser. And for other tasks as well, I have examples in the following slides, a bit of examples. So the agentic AI systems looks something like this. We have, like, it's an LLM augmented system, or we can also call like multimodal LLM augmented system these days, with MRT. And MRT stands for memory, retrieval, and tools. So when you give a question and you need an answer, we have a reasoning LLM predominantly. Reasoning is needed for planning and kind of thinking of why I should do an action. It has access to certain tools which it can call and get response from. It has access to some retrieval systems where it can query and get results, and a memory as well where it can read and write. And this is kind of not very mature yet. I think none of these are mature. These are very new areas. Maybe it only started last 1.5 years when people have been kind of scratching the surface of these. But yeah, it can solve a lot of questions. So let's give me some examples. Like if someone asks like, what's the weather in Kathmandu, and LLM cannot tell you because LLM doesn't have that information of what's happening, what's the weather measurement currently. So how it would work, like how an agentic AI workflow would answer this question is, the LLM generates certain things. In this case, it finds out that okay, it has to okay, maybe there's a typo here. So there's a web search or maybe API that takes weather from the meteorology department in Kathmandu, and the query is weather in Kathmandu. So the external tool searches and provides the weather result to the LLM, and the LLM answers the weather info in natural language. So if you use tools such as Perplexity or Google's Gemini, or these days even ChatGPT and all this have it, they will do a quick tool search, retrieve the weather result, and that give you the answer in natural language. So this is one example of workflow, and why it's called agentic is because it takes a decision on its own to uh, to use the tool here. Like no one is telling, like when I'm asking this question, I'm not telling the LLM to use this tool, but it's kind of deciding on its own that, okay, to answer this question, I need to use this tool with this query. Other examples as well. If I invest something at a certain compound interest, what do I have at the end? So if you look at these kind of questions, there's an explicit calculation that needs to be done, or in other words, program execution. So the LLM generates some code. It says that use a Python interpreter, and the code is just give me the result of this. And the LLM generates codes, the tool runs it and produces the output. The LLM answers with the result in natural language. So this is where the LLM decided itself, I need a Python interpreter to run some calculation. And there are other examples like generating some advertisement copy, translating it to a different language, writing an outline of a document, checking that the outline meets certain criteria. If it's passed, then do something. If it fails, exit. Then writing the document based on this outline. These are some other examples. These are some very classical examples of deep research. Deep research are very proper agentic AI systems. So we're just at the very early of what here is, but if you think about it, any human workflow can be converted into these, and like there are a lot of questions, a lot of aspects to like agent AI systems in terms of like how to design tools, how to train, how to do reinforcement learning based understanding, or maybe development of like models for specific tasks, how to design environments where I can simulate a lot of things. In robotics, it's going to have a huge impact. So there are a lot of things. I just kind of give a very high level overview of this. And finally, RAG, which is also like related to this, like the retrieval system is where the RAG comes. And like the key motivation behind RAG is that the LLM generated response is only based on its parametric knowledge, and which is learned during the model training. And if I want a non-parametric knowledge, it's not there and it needs to be retrieved. For example, the weather in Kathmandu, the same example, the weather was a non-parametric knowledge and it was retrieved with the tool there. Queries like these, like for example, which companies were the top market movers last week? These are non-parametric knowledge that must be retrieved, and LLMs standalone cannot solve it. It will give answers, but that will be just rubbish tokens. It won't be real answers. So to answer queries like these, we need a retrieval augmented generation system. That was one of the very first work was developed by a team from Facebook AI Research, and they had like a retriever, which is basically for a certain query, retrieve me some documents that I can augment to a generator, and the generator is an LLM. So that's why it's called retrieval augmented generation. The generator is an LLM, and I'm doing some retrieval based on a query. It's as simple as that, but there are details to it, and I would encourage checking out some of the works from V8.io, which is a vector database company based in San Francisco. They have like I mean, not they, but most of the RAG system today are industrial. So there's a lot of like recipe in terms of how to do this vectorization, how to implement search, what kind of chunking to use, filtering, all these stuffs. But there are three key components. One is how to manage external knowledge source, how to what's the prompt template, how does it fit in some context that is extracted, and how LLM model is used for the inference. So the external knowledge is stored as vectors in a vector database. So what happens is, like, let's say I want to develop a RAG system for a financial use case. What I'll do is I'll extract everything on the web about finance, or maybe if I have private data about finance, I'll also put that. I will create in chunks. If let's say I have 1 million documents, which will give me maybe 100 million chunks. Chunk is basically a sequence, or maybe it can be a sentence, or maybe a fixed length word size or token size. So this is used for maybe a feasibility of like representing a vector in a semantic concept. So I have 1 million documents, I have 100 million chunks. I will use an embedding model and store them in vector database. So if I have 100 million chunks, my vector database will have these 100 million times d-dimensional embeddings, and the embedding model here can be a sentence transformer. So this is where I have ingested my data. If there's a query, let's say who are the who was something, I don't have an example here of the shelf, but basically if there's a query that seeks some external information, so the query will also be converted into a vector through the same embedding model, and a context will be extracted based on similarity search. So for example, this query vector is, I have one query, so its vector will be 1 times d, and I have in my vector database 100 million times d. So I'll do a similarity search and I'll retrieve top k, let's say top 50. So it will give me top 50 chunks whose embedding is close to my query embedding, and I will decode the text of those chunks and I will put it as context. I will put the context together with query in the prompt, and then my LLM will generate an answer. So this is we have retrieval, we have the augmentation, and the LLM that finally does the generation. And the prompt template can look something like this, like it has a context keyword, it has a query keyword, and when the final LLM gives me the response, the prompt template will actually encode these things. Like it has the query, it has the context, everything in text, and then only I'll get the correct answer. So this system involves a lot of engineering and a lot of experimentation in terms of how what is leading to a good recall of knowledge, what is leading to a good answer, and so on. And there are advanced systems as well. Like oftentimes I can have parallel search engines or maybe parallel databases. Like I have one collection, one vector DB that has finance information, one vector DB that has, let's say, tech information. So I can run parallel agents to kind of go and retrieve information from my multiple databases and so on. So with this, we are close to this first session. The second session of the day. And the takeaway is LLMs develop emergent abilities when scaled to larger sizes, and there are criticisms to it, but there are results. I showed both of them, and chain of thought prompting enables significant performance without doing any additional training. This leads to the development of reasoning models that are significantly better for complex problem solving, which has led to a new kind of framework called agentic AI system, which can be used to autonomously execute multi-step workflows. And RAG is part of that, which extends LLM's capabilities by retrieving external knowledge that can be augmented before generation. So thank you so much for listening. We'll take a 5-minute break, and I have a second session as well where I'll talk about some of my research that I do at Stanford and I've been doing in the recent few years, which is relational deep learning. So maybe let's take a quick 5-minute here. Thank you.